Hi, welcome back to Kiersti's virtual classroom. Today we're working on learning a little bit about continental drift and the rise of plate tectonics. So, one of the things that a lot of scientists questioned early on was why we have mountains and valleys. And I'm sure you've questioned this as well. Why do we see vast landscape when we look outside? Why is Fresno flat? And the Sierra Nevadas are these high, beautiful mountain ranges. So take a minute to kind of think about that, and through this lecture you will learn why exactly we have mountains and valleys in different topography. So in the early 20th century, scientists didn't know much about how our Earth interacted with itself, and a lot of scientists thought that the continents and the oceans didn't move, that they were fixed, and that for all time that Earth existed, this is exactly how it looked, and that nothing had moved or anything like that. So their reasoning for why we had mountains and valleys was from crustal fracturing. And if you remember when I talked about Mars in our solar system lecture, that crustal fracturing can cause the rocks to either form high peaks or big valleys. And that's from the expansion and contraction of the Earth as it's heating and cooling. So when something is warm, it expands, and when something's cold, it contracts. And so as you see the Earth slowly cooling over time after the formation of Earth, where it's a hot molten body of rock, as it cools down, there is shrinking and cracking. And so that's what a lot of scientists contributed the mountains and valleys to early on. Alfred Wegener, on the other hand, was an explorer that looked at things a little bit differently. So we're going to talk about kind of what he discovered and how he came to the theory of continental drift. So on Earth, at any given point, there are a lot of different earthquakes occurring. So that's what all of these little stations that are popping up are. And so this kind of will tie into continental drift, then we'll move to plate tectonics. We'll start talking about faults and earthquakes, and they'll all kind of be interconnected. Okay, so the continents, as we know it today, have not always been the same. So throughout Earth's history, we have seen a shift in the Earth's continents. Now, this is what we know today. This is a screenshot or a snapshot of what our continents have experienced, if you will. We've had areas or periods of time where the continents have all come together and formed a large landmass or an all lands mass. One of the most popular is called Pangaea. And then right now we do have 7 different major continents where our continents are all in different locations throughout the world. So as Alfred Wegener started developing this theory, he started taking a lot of observations that he saw in what surrounded him. He did a lot of voyages to Greenland and Iceland, and he went to Greenland specifically about 4 times to measure ice thickness. And ice may sound trivial, but when glaciers last for decades upon thousands of years, they become really important to the rock record because they're basically their own ice record of atmosphere and how much snowpack you might have seen in a particular year. So he did die during his 4th trip, but he was able to successfully develop 4 different hard evidences for his continental drift theory. So I want you to take a second to think of what you think those 4 pieces of evidence to suggest that the continents are not fixed and that they do move would be. What kinds of things would you look for if you were a geologist or just an explorer like Alfred Wegener happened to be? What would you look for to figure out if these continents are moving, or if they've moved in the past, or if they've been stationary since they've existed? So if you need to pause this video, you can, or you can continue on and we'll start talking about them. So one of the most obvious that a lot of people recognize is that there is something called a puzzle piece fit. A lot of the continents look like they may have fit together at some point in time. The most notable is how the east coast of South America looks like it fits perfectly into the west coast of Africa here. And we can make some inferences based on continental shelves and those alignments to kind of line up all the other pieces, or all the other continents. So the first piece of evidence for Alfred Wegener's continental drift theory is this puzzle piece fit. Number 2 is fossils. So we won't learn about fossils entirely for quite some time in the semester until we get towards the end, but fossils are just preserved animals or preserved species, and if they are found in a particular region, that tells you something about what environment they lived in. And one of the things that's interesting is there are several fossils that are found on separate land masses. So for instance, we have the mosasaur here, which is this swimming guy. He's kind of like an alligator type of creature, and he is freshwater. He's a reptile. He's freshwater, which means he can't swim across the Atlantic Ocean. And as you know today, South America and Africa are separated by the Atlantic Ocean. So in, millions of years ago, when the mosasaur existed, did he swim across the Atlantic Ocean? Or was there a land bridge between those two continents? And so this was one of the real important theories, because fossils and prehistoric animals did not have the capability of crossing large seas and land masses that we do today. So using some of those different fossils that are found on separate land masses helps indicate where we might have found, where the continents might have sit previously. So this is evidence number 2. Evidence number 3 would be rocks. So in a particular mountain building event, which we call an orogeny is just a mountain building event. When mountains are built, generally the chemistry, the age, and the composition of those rocks are fairly similar. And we found rocks along the Appalachian Mountains on the east coast of the United States, and in some of the mountains in Africa and up into Europe correlate with each other. They look like they're about the same chemistry, they have the same rock composition, and they're approximately the same age, which means they formed around the same time. So that being said, that means that those land masses might have been connected at one point in time. So rocks will tell you a big deal of what the continents looked like previously. And then the 4th is climate or glacial evidence. So what's really interesting about glaciers is they do leave behind particular features or deposits that indicate that the glacier existed at some point in time there. So there are things called like glacial moraines or glacial erratics. So if you go to the Canvas page, the first picture that you see there where there's a kind of a perched rock in Yosemite, that is a glacial erratic. That is basically a pebble. It's obviously a boulder, much larger than a boulder, a piece of something that was stuck in a glacier as the glacier moved over the landscape, and it dropped it off as the glacier receded or melted. And so things like that give us an indication that there was a glacier there at some point. And because of that, we've seen glacial evidence in Africa and South America, which is really close to the equator. And as we know, glaciers cannot really form in areas that are hot, right? So you need something close to the poles or a really high elevation in order to see glaciers form. Well, if we see glacial evidence in Africa or South America, that would indicate or give a really good indication that they might have been closer to one of the poles, where maybe Antarctica is, at some point in time. So that gives us our 4th piece of evidence there. Okay, so just to reiterate, our 4 pieces of evidence from Alfred Wegener is the puzzle piece fit, the fossil evidence, the rock evidence, and the glacial or climate evidence. Okay, so he had all these pieces of evidence, and he was really sure that this is what was happening, but he didn't know how to explain it. He had all of these things that he observed happening, but he didn't know how they were happening. So he was missing the mechanism behind the actual theory. So he has his theory of continental drift, and to get to the theory of plate tectonics, he needed the how. Okay, so we're going to kind of discuss how the how came about. But first, we need to know something about the interior of the Earth. So inside the Earth, we're not just one solid rock. There are different layers to our Earth. Okay, so we have three main layers, and then we'll kind of break it up from there. So our three main layers are the core, the mantle, and the crust. Okay, the crust is what you stand on, the mantle is below that, and then the core is the center of the Earth. Okay, so let's start with the crust. The crust is where we stand. So we have continental crust and we have oceanic crust. I'll talk a little bit more about that in a second. And then below that, we get into something called the lithosphere. So the lithosphere is the crust and the uppermost solid mantle. So the mantle is this very vast, thick layer, and it is segmented into three different parts, the upper, the middle, and the lower. And depending on where you are in the mantle, you will see a different state. So closer to the crust, it's going to be solid, and then as you get closer to the core, it's going to be more molten. Okay, so the lithosphere is crust and upper mantle, which is all solid material. Okay, so that's a term that includes the crust and the upper mantle. Then below the lithosphere, you get into the asthenosphere. And the asthenosphere here is molten, so it's a little bit gooier. It's not solid rock anymore. It's more like a Laffy Taffy, okay? And this is what allows the crust or the lithosphere to actually move, and we'll talk more about that in a little bit. And then below that, you just have regular mantle, and then we have the outer core and then the inner core. The outer core is liquid and the inner core is solid. All right, so let's talk about the crust a little bit. So I did mention that there is oceanic crust and continental crust, and they vary slightly. So the continental crust is thicker, which is why we don't have oceans covering much of the continental crust. And the oceanic crust is thinner, which is why that's where most of the water sits. So it's at the low point on the crust. The continental crust is much more buoyant, and it is less dense than the oceanic crust. So the oceanic crust sinks below the continental crust when they interact. We'll talk more to that a little bit. But just make sure you're aware oceanic crust is denser than continental crust. Okay? And the oceanic crust is much younger than the continental crust. Okay? So what is the crust made of? So normally in a class, I would have you look at rocks, just look at the pictures for now, and try to distinguish which one you think might be oceanic crust or continental crust. So you can write down some thoughts, think about it. I will tell you that this one on the top here that's all black, that one is much denser than the one on the bottom here, which is black and white. In a particular class period, you would actually be able to feel this in your hand, but use the photos and the information I've given you to kind of think about that, and then we'll move on. Okay, so the one here at the top is the more dense rock. It is basalt. It's an igneous rock. Actually, both of these are igneous rocks. But the basalt would be your denser crust. So this would be your oceanic crust, and this one here on the bottom would be your continental crust. It is much lighter. So most of the oceanic crust is made up of basalt, and most of the continental crust is made up of granite. So basalt is spelled B-A-S-A-L-T, and granite, G-R-A-N-I-T-E. So granite is continental crust, basalt is oceanic crust. So this is in general. Okay, so how do these solid rocks actually move in real life? So to understand kind of how the continents might move, we need to understand what would maybe drive them. So a good example would be a lava lamp. Normally I would have a lava lamp set up for you to look at, but I think most of us have seen a lava lamp perform and what they kind of look like. So here's a picture for you. How do you think the lava lamp actually works? If you're not sure, you can take a second to try to figure out what you think might be happening. If you've never seen a lava lamp before, here's an example. It's the blobs of orange will start here at the bottom, and then eventually they'll rise up, and once they get towards the top, they'll start to fall again. Okay, and that's just kind of the cycle that you'll see a lava lamp take on. Okay, so take a minute and see what you think. Okay, so the way that the lava lamp works is there is a heat source at the base. So let's go back and look at that for a second. So we have a heat source here at the base, and it heats up the oil, which is this orange stuff, and then there's resin as the purple stuff. So it heats up the oil, and when something heats, it will rise. As it comes to the top, it cools down and becomes more dense. Because it becomes more dense, it ends up falling. So this is a heat transfer method that we can see even in the basic form of a boiling pot of water. This is the reason why your pot of water will boil. So we have three different types of heat transfer: radiation, conduction, and convection. Radiation would be like receiving heat rays from the sun or rays of heat from a fire, a campfire or something like that. And then conduction is when you touch something and it's hot. You feel that heat transfer into your hand or whatever body part actually touched the hot pan. And then convection is what's happening in the water or in the boiling pot here. So we have a heat source. Obviously, the burner is our heat source. The water that's closest to the burner heats up first. And when it heats up, remember, it becomes less dense, so it's going to rise. As it comes towards the top of the pot, it cools down again. When it cools down again, it becomes more dense and sinks. And so you see this cycling, and when you have a bunch of little convective cells in your boiling pot of water, it creates bubbles. And so you see boiling water. Okay? So how does this translate into the earth? Well, as I've said before, as you get further down into the mantle, it gets a little more molten and things can actually move around. In that case, you have this center core that is really hot in the center of the earth, is acting as your heat source. So there's something called mantle convection that is where the mantle material is being heated by the core down here, cooled by the crust, and forms these convective cells. So the mantle is hot iron-rich rocks, and the texture is behaving like an elastic solid, and it flows in these convective currents. And this convection, mantle convection, was founded by a fellow named Arthur Holmes in 1928. Okay, so then we get into the core, which is liquid iron and nickel at the outer core, and the inner core is solid iron and nickel. And the reason that the inner core is solid and not liquid is because it's under so much pressure, liquid cannot flow at those pressures and temperatures. So you see a solid, basically, rock of iron and nickel. The outer core, however, flows at several kilometers per year, and the flowing motion creates the magnetic field, which we'll talk about in a little bit. Okay, so one of the next things that happened after mantle convection was sonar mapping by this guy named Harry Hess. And so around World War II, we were using a lot of sonar technology. And we used sonar mapping to map the sea floor. So what they would do is they would take a boat out into sea. They would send down a signal, or basically a sound, and it would hit the bottom of the ocean floor and bounce back. And so this was really important in furthering the development of plate tectonics, but also understanding what the seafloor looked like. For a long time, a lot of people thought seafloor was flat, right? When you put water on top of some soil outside, most of the time what's below it, the topography, is just flat. So doing the sonar mapping, they found some really interesting things. One of those interesting things was the mid-ocean ridge. So in the middle of the Atlantic Ocean, there is a ridge, and in the middle of the Pacific, there's another ridge, which we'll show in a second. So as they came off the continental margin of North America, they saw a definite dip, which is what they perceived the entire ocean would look like. But then once they got towards the center, they noticed that the sound waves were coming back faster, which means that it's a higher topography and you're no longer at a low point. So then that's where the mid-ocean ridge was found. And then there's another deep ocean basin before you get over to the coast of Africa. Okay, so it revealed that right in the center of the ocean, there's this very large ridge, still submerged beneath water, but there's this ridge down below the ocean. Okay, so between the 1940s and 60s, Harry Hess started kind of connecting all of these dots, connecting things that he saw from Arthur Holmes and from Alfred Wegener, and he developed this theory called seafloor spreading. So he echo sounded the seafloor, which showed him the seamounts and the topography at the mid-ocean ridges. They did note that at the ridges, the temperature was a lot higher, and they did notice volcanic activity. And this appeared to be the younger material. So the thickness of the sediment that's actually accumulated on the ridges was very thin compared to the basins. So he also suspected that the continents did not actually plow through the oceans. So after continental drift, a lot of people were surmising that maybe the continents moved, but the oceans didn't. So that the continents sort of floated on the water and moved around. But that's not what Harry Hess thought after doing some research. So when we combine Harry Hess, Holmes, and what Alfred Wegener developed, we see where the continent and ocean meet at the trenches, the ocean is being returned to the mantle at the same rate it's being generated at the ridges, or henceforth developing this seafloor spreading theory. So let's take a look at the diagram. This will kind of show you the all-encompassing what's happening at the seafloor and what's happening with these convective currents. So here we see two mantle convective cells, and they're going in opposite directions. So this one here on the right is moving in a clockwise direction, and the one here on the left is moving counterclockwise. When convective cells move in different directions, they start to pull whatever is above apart. And that's what we're seeing in the middle of the ocean, is this pull apart, and then material starts to fill in, which would be the development of a ridge. So material is being created at these mid-ocean ridges, and then where this crust or this lithosphere is hitting the continental lithosphere, you see it return back into the mantle as it's dragged down by the convective cell. Okay, so these are just cycles. So we're pulling apart at the top, and then it's being taken back down into the mantle at the continents. Okay, so to further this theory of plate tectonics, as we start to get further and further away from just continental drift, now we're talking about plate tectonics where we have plates all interacting with each other. So this is the snowball after the seafloor spreading storm, essentially. So before we start really talking about how we got ages and things from the seafloor, we need to know something about paleomagnetism. So paleomagnetism is the study of iron-rich minerals in rocks that have been magnetized by the magnetic field when they were crystallized. So when a rock forms out of a lava, there are magnetic minerals or iron-rich minerals that will magnetize themselves and align to magnetic north at the time of formation. And we do see flips every 300,000 years of our poles. So right now, magnetic north is where geographic or true north is, right? But over time, the magnet flips, and we see magnetic north become true south, and magnetic south becomes true north. So the way that the magnet works around Earth is the flow of the liquid outer core and the interaction of the inner core that's solid allows for the magnetism to occur, and it basically turns Earth into a giant magnet with a north and a south pole, just like any magnet would have. And the magnetic field around that magnet flows from the south into the north, just with any magnet, right? And in a reversal, it would flow in the opposite direction. So your rocks would point in a different direction, depending on where magnetic north was at the time of their formation. Okay, so take a look at this diagram. This is going to kind of go over how we relate seafloor spreading to paleomagnetism. So look at these three diagrams and then kind of think about what you think is happening, and then we'll discuss. So you can pause the video now and think about it, write down some notes. and then we'll talk about it. Okay, so what do you think is happening? So here in period A, or time A, excuse me, we have a normal reversal, and you see magma coming up and filling in this void as two plates are moving apart, okay? And then in time B, we see a reversal, and we see more material coming up, and you see the arrows changed direction, right? So that was indicating that the true north is, or sorry, magnetic north is no longer where true north is. We have a reversal here. And so you see them shaded a little bit differently, and the arrows are pointing in a different direction. Okay, and then time C, we see normal magnetism again. So we have magnetic north is where true north is, and you see the flip of the arrows once again. And you kind of see these stripes being formed. So the stripes, if we lay that across all of the seafloor, give us a really good indication as to how the seafloor is actually spreading and how things are actually moving. So in the center, we have a ridge that we talked about, right? And that's where all the youngest rocks are. So if you look at this map that's created using paleomagnetism, we see all of the youngest rocks at the ridges and all of the oldest stuff closest to the continents. And they are symmetrical as you move from the ridge. So whether you're going east or west from the ridge, you see a symmetry. So you see the same age rocks with the same orientation to magnetic north as on the other side of the ridge. And so that just further indicates that material is being created at the ridge and then being spread apart. Created at the ridge, spread apart. Okay, so this really didn't come up until the 60s, which is really interesting because a lot of people think that geology is old because the Earth is 4.6 billion years old, but a lot of the theories that surround geology are not that old. I mean, you probably have parents or grandparents born in the 60s, and so you even know somebody that's still alive since then. So these are very new ideas, relatively speaking. Okay, so I already said the youngest rocks are at the ridge, oldest are up against the continents. So if we look at a map across all of the oceans on Earth, you look at something like this where we see all of the ridges at these very dark reds, and that's where all of our youngest new rocks are being formed. And the oldest rocks are all up against the continents. Okay. So with that, we'll look at the different tectonic plates. So there are a lot of different tectonic plates. Some are very small and some are very large. So we have the North American plate, which is where we lie. If you go over to the coast of California, you'll also be able to stand on the Pacific plate. So you can stand on another. If you go up into Northern California, you can go up and stand on 3 different plates at one time, which is pretty cool. The plates, all these arrows here are showing you their interaction. Are they coming together? Are they pulling apart from each other? Or are they sliding past? So the next lecture you'll see is the interaction between the tectonic plates and how all of that works and what that forms. This was just the rise and development of the theory. Okay, but before we go, let's look at the 7 major plates. So North America, South America, Eurasia, Africa, India, Pacific, and Antarctica. So the Pacific is the largest, although on that map it doesn't necessarily look like it. If you look at an actual globe, the Pacific is stretched much larger than the North American plate, or even the Antarctic plate. So remember, these 7 major lithospheric plates we'll talk about a lot, and we'll talk about some of the smaller ones as well. So in summary, we talked about the continental drift, which was founded by Alfred Wegener, and we talked about his 4 pieces of evidence. Seafloor spreading and mantle convection led to the rise of plate tectonics. We also talked a little bit about the Earth's composition and that the continental crust is much less dense than the oceanic crust, which will be important for interactions in the next lecture. We looked at the map of the seafloor, which used sonar mapping to determine that there was young material at the ridges and the oldest on the continents, and then we reviewed the 7 major tectonic plates on Earth. So I hope that makes sense, and I will see you guys in the next lecture.